Are you gonna send that?
No.
Okay. I figured it was a no, but I know it's so.
So it's the question.
Or the Monday following.
Suppose you have 5 people, you print out, you mark them.
Yes.
Or
This one
I
was-
can't file
this is the old
my
side.
But also, I want papers so that I can. Wait.
Oh, that's
Yeah, that makes. Wait, it's what?
9th week.
Oh, yeah, that makes sense. Because we're third.
I'm assuming though.
So then maybe they're doing both the presentations on Monday.
The next one.
Well, she came, you went to like 12.
So are both presentations next week on Monday? Isn't the test next Wednesday? Or no, it's the 20th. Never mind. Okay, sorry.
Here we go.
We're still 2 weeks from today.
You have 1 day for review.
Okay, so we'll do the review that Monday.
So you have 1 day to
So I'm counting. Dot the i's and cross the t's. Cross the i's and dot the t's.
Oh.
Backwards. Yeah, I was thinking, you were like, I'm not gonna go into the test where it's like, dude, that's when they drop the bomb. Yeah, that's honestly valuable. I think it's one thing that I will do is like show up to class. Like affect that more than anything else. Like show up and like fire and pay attention. And homework. Yeah, most of it.
We're the last one, but it's like we're pretty glad. We have an extra week.
That's good. That's good. I've never really used that Zoom before, but pretty good like a Zoom project. Like it's nice to kind of be able to all work on the same thing, but also like you're in your own space.
Yeah, Zoom was cool.
So, first announcement. So you need a phone group again. This time you are volunteered from your own group. Maybe 2 students. 2 students as a group. Okay. 2 students. So I think one voice will be announce among everyone. So announce again. So once your phone group send me email about a group member. Each group only the 1 person.
When do we have to figure that out by?
You need to figure out as soon as possible. So if you figure out, which means before we count, before on 3. So I will give you a paper then. Because right now you don't know which group you are, you don't know your presentation order. So if you have the first paper, which is your the first. So maybe it's a good idea to form the book as soon as possible, and then I can give you paper as soon as possible, so you have more time to read. Good. The second announcement is, I think I want to see my Monday, it seems like because this class, this is the first time I teach this class, the design class. So the first time is different from the second. So especially the first part. So basically the first part is the computer redesign system. So that all the lecture notes, all the homework, all the pre-call, all the homework, it's redesigned. In a way, I think because I want to bring you to both one view in terms of scientific. So as maybe you already knew that, everything is real. Maybe you never thought. Makes sense? So we try, for me, for this class, also I redesign for all of the first part. Because I believe you learn cell biology, makes sense for most of the students, or general biology, or biochemistry. But for me, I think maybe one of the main purposes is to try to expose you to frontier the concept and also gene regulation. The kinds of what you will see is most of it is the new idea, new concept. It's not an old one. Makes sense? You cannot see in the textbook. So which is in terms of exam, also the first time it's my first attempt to do this kind of exam. So which means we have practical application, you know that. So which means you should practical. You should able to do all the practical application. You should be able to understand the practical application. You should be able to do. So which means finally maybe we will have one question that will try to integrate most of our practical application by scientific research. So which means we design one question and then we step by step with all your methods. Make sense? Yeah? I like that because personally, one can really tell you know something and then you can use that something to solve a problem. But personally, I like that. That is a practice. And also maybe they have some short answer, which means that should come from the question in the lectures. And I think for most of the questions we have extensive discuss. You discuss by yourself in the group, and then I also give you answer. Finally, I think that's completely new content for my this class of environment teaching. So which means you will have 5 papers. Those 5 papers that have been presented. Well, So you need to print out that paper. You need to print out 5 papers. I believe you should print out because each time you read them. So which means during the exam, you can bring that paper together with you. Bring that 5 papers with you. How many questions we have? I still think how many questions you should have from the paper. So right now I think maybe it's 1 question from 1 paper. one question from one paper. So which means the question should embed in the paper and you did find out. Maybe they already mentioned in the lecture notes or when they present. Make sense? Or maybe you didn't find more precisely how they did explain or how precisely define the terminology. Right? So the here, which means it's open. Open question. Actually, I think one question.
So it's one question per paper, or one question
One
about
question
one
for
of the
paper.
papers?
One question per paper. So which means you will have 5 questions. This is, as I already told you, this is my first time to try to do this. If you like it, tell me. If you don't like it, maybe next year I will change.
How many questions are there total?
That I'm still thinking.
Still deciding.
Yes, you have one. So which is how many questions? So like here, I think maybe I want to put 80 points. Right?
Just there. Okay.
Yeah. And here we can have another 50 points. Right. Any question? Do you like this format?
We'll see.
Sounds good. Promising.
It's good on chalkboard, but
But then again, I hate open world tests because I always like the hardest.
Yeah, that might screw you.
Any question about the exam? No? Good. So we continue. We continue post the transcription process. So we talk about coding, we talk about coding structure, we talk about transcription. In terms of transcription, we talk about epigenetic factor, how epigenetic factor can predict transcription. And then we also talk about basal transcription machinery, and we also talk about promoter and instrument. That's all of its transcription. Okay. And then I will basically briefly talk about post-transcription process. In terms of all the disease and the development, the major driving force is still from transcription. Right? And of course, this kind of process also is very important. You cannot exclude it from this process. For post-transcription process, they include quite a few steps. Actually. So, for example, here is a gene. Within one simple gene, they have here is a regular sequence. Also, you can say another terminology. What it is? Yeah, promoter. You can say co-promoter, and also have upstream promoter. Right? So basically, they call regular sequence. It's a promoter. And here is starter size. Right? So it's that one. The starter size is determined by promoter. Right? It's by basal transcription machinery. Make sense? Basal transcription machinery will determine where should start. The efficiency will be determined by transcription factor. Well, like this, for example, enhancer. And also you have, in terms of one gene, you have exon, and also have intron. And also have termination sequence. Because in terms of genetic information flow, the how to start at specific sites. Because in terms of entire living organism, we always say they have specificity, even for human beings between different persons. We have specificity. That's why everybody have talents, have your own talents. Right? So that's why you have to specific. The start specific size and also the end of specific size. That is determined by DNA sequence. Right? The encoding DNA sequence. And the DNA sequence, of course, they can interaction with the transcription factor or other proteins. Right? And determine where to start, where to end. And then there were transcription in the mammal, in the eukaryote. Therefore, here we call a primary transcription. And in the primary transcript, as you can see, they have intron exon, right? As you know, intron do not encode proteins, right? So which means they will remove intron. In terms of eukaryotes, actually, the first step is add the cap. Because once you start transcription, and then you will have 5' end, you will add a cap. So they will add G here, G here. And the G also have been modified on position 7. It's methylation. And this is the cap. The cap is very important because the cap will coordinator, they will protect mRNA from degradation. Also, for eukaryotes, actually this cap also is recognized by initiation factor. Right? So which is initiation factor will bind to here and they will search the start codon. Right? And once start cap at the same time, there also was splicing, so we will splice out the intron. Here, the intron. We will remove the intron. And now we will produce a mature RNA. We will produce mature RNA, also called messenger. We will produce mRNA. We will produce mRNA. And the mRNA will transport into cytoplasm. Because here, this step is within the nucleus. Now, from the nucleus, it will transport to cytosol. Within the cytosol, they have a ribosome, which is the ribosome will start translation. And all of this steps can be regulated. It can be regulated. It can be a different way.
Is that the same if it's going to the ribosome?
So the ribosome is attached to the ribosome.
Yeah. So it's still the same flow.
No, I think the RNA maybe have specific how protein binding to the mRNA, and then this one will transport into cytosol. It's not a particular
So is it like a special restriction enzyme that cuts the RNA, or what actually takes the section out?
So they have dependent, like for all mRNA degradation, within the cell is not random. They have a specific mechanism to degrade the RNA. They have like some like P guanidine, so they will specifically put it into some guanidine. But guanidine has control open. They still put it in a specific position to degrade the mRNA. It's not random. So the first step is copying. Because the copying is quite important because, as you know, within the cell there have so many nucleus, RNAs. So RNAs can cut the mRNA either from 5' to 3' or 3' to 5' or in the middle. Right? So which means most of the time when you cut RNA, it's either from 5 to 3 or 3 to 5. Right? So which means you need to have some mechanism to protect mRNA from RNAs. Right? That's why there are the guanine base here. So like 7 marker guanine here. Here they call 7 marker guanine because here the position 7 have been marked. Right? And also here the link is 5 to 5. So normally when we talk about RNA, it's 5 to 3. Right? So it's not here. It's here is the 5 position to 3, and here the first SFR to 3 to 5. Right? But here is kind of different. The whole 3 was very hard. So and then sometimes our position here, position 1 and the position 2 also like the 2' OH also be masked. Right? That is also they try to make RNAs not recognizable by RNAs. Right? Another thing that we talk about, the provide the binding sites for initiation factor. So which means the initiation factor can bind to here and increase the translation efficiency. And here is the mechanism how 5' can copy. So the first is the guanine transcripts, and then you have guanine marker transcripts. So when we talk about this, the copying is enhanced translation of mRNA by ribosome, and also protect the 5' of the mRNA from the touch exonucleus. Exonucleus, which means that they refer to 5' to 3'. Also, you have 3' to 5', and also have endonucleus.
So the cap in this case is the guanine base, the methylated guanine base?
Yeah, it's here.
Is it always going to be guanine?
Yes, it's always the one. It's one place. That's a 5' copy. And also you have poly A tail. So here, so once the transcription reaches to the end, so here is the poly A site, so which is the poly A you add to here, and then before upstream of the poly A site have specific sequence. As I just told you. For transcription for genetic information flow, the initiation and the termination, they have to start at a specific site, end at a specific site. Right? That is coded by DNA sequence. Right? So here is coded here. This sequence will bind CPSF will bind to this sequence. Right? And another protein called CSTF will bind to another sequence. Now these two proteins, they can interact with each other and form looping. Looping is quite important, right? I think a lot of you students talk about looping, but it's a two protein, the touch and looping. Right? Because in biology, as we talk about in genetic information flow, because if you think about DNA sequence is very long, right? How they can function together is by way they looping. Right? That's why For most of the mechanism we see in textbook, right now we say looping. Right. It's looping. So once the looping together and they were exposed here, and the nucleus will come here and cut here. Right. Once you cut, they will dissociate this part, and this part will get a degree, and the other parts will cut poly. Right. So still the same. So in terms of polyadenylation, enhance the stability of mRNA and also the transcription. Because if you have poly A and the endonuclease cannot easily come from here, from 3 to 5. Right? Also, they will increase the transcription.
Why you need to form a looping? Because if the looping isn't formed, so the enzyme is cut in the half of in the middle of the.
Yeah, we need the looping. If you think about the looping, which is the so looping is a mechanism to know. Okay, if I have two binding together, they know. Okay, we should stop the transcription now. Make sense? Right? And then also they present this site for carbon. Because other the iron polymer is still here.
Is there a specified length for the poly tail, or is
So if you say here, this is 200.
right? Is it limited to 200?
But no, it's not necessary. So they have variable. So they have different things. Right.
Is that regulated, or is it?
It also is regular. Yeah. So here the length also be regular, short or longer. Right. Also a specific factor. Right. Because that here they still can regular move. One thing is they can regular degradation. Right. Because as a degradation either is 5 or 3. Right. So once you don't need a protein, so of course you degrade the mRNA. So which means you have how much kind of to recognize that you have degrade.
So this process is just coding mRNA. Is it the same transcription process for non-coding mRNA? Is it similar or is it different?
Non-coding RNA depends on what kind of non-coding RNA you talk about. Most non-coding RNA they don't have or poly. Most of them sometimes don't have CAR. The nucleus.
So they stay in the nucleus?
Non-coding RNA depends on what non-coding RNA you talk about. That is another topic. Non-coding RNA, some of the non-coding RNA will stay in the nucleus. Some non-coding RNA will in the cytoplasm. Some even like micron or 40. They even go to blood. They have more mechanism. Also in terms of non-coding RNA regulation, I think that now school. Right. It's not like here. We have been studying for more than 30 years. Non-coding RNA just 10 years. So which is we still have not. So that's why we did not add in. And then we can understand. So also, so you have copy and the polyadenylation, and also you have splicer. Right? Splicer. Splicer is by spliceosome. Splicer also is not random, it's tightly regulated. Right? It's sequence specific. Right? It's cell type specific, sequence specific, development stage specific. Right? Also is a physiological condition specific splicer. It can respond to intro or extra cellular signal. So splicing, how they define the size for splicing, they use 2 RNA U1 and U2. Right? And here you can put out non-coding RNA. Here you can code non-coding RNA. So the U1, U2, and here U1 will plug into 5 exon here, 5' exon. And the U2 will bond to 3' exon. So now, which means they will mark the splicing site. Like here is GU and AG, which is they will splice from here, and they also will splice from here. Well, they will mark the splicing site. So here is the mitochondria. So complete mitochondria. So if you look here, the U1 will bind into here, GU, the base pair. And the U2 will bind into here, the base pair. So U1, U2, and once U1, U2 bind, and then they will have U4, U6, U5 bond. Now the form looking again. I think that the first talk in terms of genome organization have looping, and when over East chromosome also have looping. I think if you look at previous, that's the whole looping, and here they also have the looping. So now they have the looping and put together the distal sites. So basically, in terms of the genome, you have distal sites. How the distal sites can interact with the proximal sites. That's both by looping. So and then they were looping together, and then there was remove the intron and rejoin the exon. And in terms of splicing is also very important because splicing they can so for some mRNA they have hundreds of intron exon. So if you think about like combination, how many proteins they can generate? So one of the, let's say some mRNA or some RNA can generate 10,000 proteins. Right? Because that is combination. Splicing.
So is there a connection mechanism so far during the process because there's a lot of mistakes in transcription and transmission?
Yes, they also have conventional mechanism. So for example, if this pair is constant, so here is basic mechanism. But in terms of which sites to which exon to which intron to splice out, how to join them is by specific splicing factor. Right? So which is specific splicing factor will bind to specific sites, and then they will join them exon together. Still pattern record. Okay. So here in terms of transcription and post the transcription process is coupled. So it's technical coupled. This here, RNA polymerase is the central machinery. So here, this one will determine when we're splicing, when we're at a cut. So still by RNA polymerase. So for example, for the copying, so here is a copy enzyme. They will bind to RNA polymerase. They will bind to RNA polymerase, and then copy here. Right? Once the finish copy, and then the enzyme actually here is the phosphorylation. So the first phosphorylation will recruit this one. We recruit RNA on the copy enzyme. So here actually, do we talk about CTD in this class? No.
C-terminal domain.
Huh?
C-terminal domain.
You're right. C-terminal domain. So RNA polymerase they have a C-terminal domain. The C-terminal domain is a repetitive sequence. That sequence can be modified, can be phosphorylation. So the first phosphorylation, So without phosphorylation, which means the ion polymer will stay there. Right? Once the phosphorylation, which means they will tell enzyme to start. So which means once it starts, you will produce mRNA. Right? So at that stage, you will copy. Right? So now they will get a phosphorylation. So once they get phosphorylation, and then they will record C copy enzyme. And once from the initiation to elongation, and then the CVD can get phosphorylation again. Right? And that phosphorylation will record another complex SC, so which means the splicing complex. Right? And then the splicing complex will remove here, and finally they will record the polyamine complex. So basically what I have in terms of RNA polymerase is the CTD, actually it's the signaling center.
Serine phosphorylation.
They have both serine and like here they talk with two. They have two serine phosphorylation and 5 serine phosphorylation. But that actually is 7 peptides repeat, so which means they have lots of serine and serine. Right now we know it's 2. First is position 2, serine phosphorylation. And from the initiation to elongation is a 5. So but actually in reality it's much more complicated because they also recorded lots of other enzymes. For example, like epigenetic. Also it is recorded by CTP. Epigenetic enzyme, kinase, and histone modification enzyme. Right? Many different kinds of that. It's a full city.
So
So we have this last.
capping, protection,
Come up
polyadenylation, export from the nucleus, splicing, genetic variation, isoforms or whatever.
Did you see the polyetail is for transport?
Excellent.
Expert movers.
Which
I have a
And splicing is just to change expression.
you wrote the
well.
you just said
So what he was saying is that you can have a protein with like exon 1 and exon 3, or you could have a protein with exon 1, 2, and 3, or no. So the alternative splicing produces protein isoforms, which is what something we'll talk about today. How interesting! How fun! I think it'd be okay with the rest of the reader.
Oh,
Something on that.
Very good. I'm just going drop your wallet. Could have killed me.
I usually just try to find all the slides and but he has pretty vague and ask additional questions for it. You didn't discuss the mechanism or the structure or its functional role or something like that.
Yeah, that's easy. Yeah,
It's always the easiest way to do it for me.
I don't even think he reads these. I think he just,
He just gets the points.
yeah.
I've been getting all the points on this.
That's the way to do it. That's why you're gonna get A in this class. So, 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 so,
So half is a 5%. Or 8.
Functional splicing did you put?
So it's like alternative protein isoforms. So you can have a protein with an exon so the alternative splicing you could have like exon 1, exon 2, exon 3, or you could have exon 1 and exon 3, or exon 1 and 2, or 2 and 3, or just alternative splicing for different protein isoforms. I'm pretty sure. That's why they if they ever ask you if you have the long form, or if you ever hear about people talking about the long form of a gene or the short form of a gene, it's like alternative splicing. And so the long form is less likely to be inhibited by microRNAs and degraded. So if you have a long form of the gene, it stays in your bodies. Like that gene is more expressed or active, or that action is more if you have the long form. But if you have the short form,
What do you mean by long form? One is a long form like structural variants, like you have repeats, and you have like a lot of repeats. That is wild. Like supposedly that's why dogs really easy because they have like massive numbers of these tandem repeats. And so like when you breed them, it like mixes the tandem repeat numbers really well with the offspring. So that's why they have such a phenotypic diversity, even though they're like really related. Like it's a lot on a German Shepherd, they're like the same thing. They're the exact same thing, except like one's that, the other one's that. It's really just different numbers of tandem repeats.
that's super interesting. Where'd you hear that?
That's just breeding shit.
You know a lot of I feel like you've been talking about that all day, dude. I feel like what? This is not the only time you're talking about dog breeding.
A lot of standard tandem repeats.
So do you have answer for all of them? What's the function of the binding?
Protecting the end of the RNA.
Okay, and then?
Protection,
Site for binding of RNA polymerase.
No.
Or enhancer,
Or the
initiation factor.
It prevents the attachment of the exonucleus.
Okay. And
It prevents segregation of animal RNA.
so it's you have.
Doesn't it recruit the initiation factor?
Yeah, that's why you can say enhance the translation efficiency. Right. So enhance translation efficiency protecting everything. And what's the function of polyadenylation?
The stability and also helps bind the
Yeah, so also is for we didn't talk about actually for mRNA the translation in eukaryotes they form a circle. So that's why you find out the three both have that function. So mRNA is a circle. Okay, good translation. Which is like this. So the 5 here and the 3 here is also like this. They form a circle. Must make sense, right? So it's both have a function. Because of course, circle is easy. Because once the finish, yeah, the values are convenient jump away. Well, if you are like this, then some mRNA is 2 kb or 3 kb, 5 kb. So which means you jump is not easy, right? But that's why they form a circle. It's easy to jump. And also, you can start about why the following. What's the horizon? Another answer?
Alternative protein isoforms.
Yeah, so basically that is they can increase diversity of mRNA produce more different protein. Right?
Are those proteins ever like 100% unique, or are they just kind of like similar to each other? Or do they do tons of different things on the same gene?
That's a good question. So in some case, they produce completely different protein. Sometimes they produce similar function protein. Sometimes they change some domain. Right? That will regulate different process. So that's why I say splicing is cell type specific. Right? So which means in one cell type they will generate one protein, in another cell type they will splice out to generate another protein. That process is controlled by signal pathway. That often happens during the development. Or maybe the people are having conflict or from that out from how many design. So maybe also that's just I don't know.
So when they slide, when the splicing happens, all intron will slide or just some, and then it leaves some.
So what the intron is first out? On the join, the hidden join. For example,
Is that
you have piece 1 and piece 2, 3, 1. So here is the intron, here is intron. Intron 1, 2, 3, exon 1 primer, 3 primer, 3 primer, 4 primer. Well, so all the intron will be removed. But the join, maybe they will have different join mechanism. They can join this one, they can join this one, they can join this one, right? They can join this one, this one. They can join this one, this one, this one. Right? Yeah. So you can think about how many parts in the house. They can, and now we can join this one, this one, this one, this one. Right? You can start from 2 again. So it's a combination.
So in the case the one prime join to 3 prime, so they gonna split out the 2 prime.
Yes, there was splice on 2 parts. We completely splice the 2 parts, which is one. If you think about the splice, which is like here. So which means if the join here, so which means the splice in how this unit. Well, they just skip this one. Any other questions? No? Okay, without a question, this work can move for you. They will talk about sometimes. I think it's interesting. Hope you also enjoy. Yeah, there is a point. Yeah.
Oh, this guy's.
Yes.
Cool.
I was gonna stand over here.
So there we are. Hi. We're staying.
Clickers to last.
Switch me.
Maybe you can start.
I know, I'm standing over here until my section.
Will it work?
I need to.
Does this click? Can we click this? Our friend has.
It's also over the way marketing sweatshirts and those are cold. I get that extra. It's like it's so warmer. It's somehow.
It's gonna smell.
I think maybe you can start.
Good evening, everybody. I'm Sean. This is Chase, Stephen, Brett, and Emily. And we'd like to talk to you about some research that Peter O'Donnell and others performed on characterizing the major structural variants alleles of the human genome. So first what we'll do is we'll talk a little bit about what it was that they discovered. So the work that they were working on was the human genome reference. So they actually have a reference out there that they can compare human genomes to, compare different aspects of different genomes, just a reference to have. And then part of what they discovered was structural variants within the different human genomes. And so something that we'll discuss with you guys is the different properties, the different qualities, what they are, the significance of these structural variants. So first off, we'll just do a little bit of background on what the current human genome reference is. So the current one is called the GRCH38, and that just stands for the Genome Reference Council Human Genome, and this will be the 38th copy of it. So this sequence was put together from a number of different individuals, but the most important part is that about 70% comes from one individual haplotype. So there isn't a whole lot of variation or representation of human species within the reference genome. It was assembled mostly from bacterial artificial chromosomes, so it was propagated within E. coli, and so the E. coli mechanisms was used to amplify the DNA inserts. And so there's various problems that they ran into using large amounts of eukaryotic chromatin that they were producing. This genome, the reference genome, was introduced in 2013, but since then, with increasing technology, they've been able to make modifications, corrections, expand it, and so that is a continuing process. But even so, there are still problems, just to be expected. Technology is still catching up to what the entire human genome is made of and all the information contained within it. So, it's to be expected that there's going to be gaps, pointing to errors going on, but the most important part is going to be the general diversity of the human genome reference. So a solution that the group proposes is to produce a canonical reference genome. And that's to say that, in essence, the perfect genome, if you will. No errors, no gaps. Just technology progresses, we can get closer and closer towards. But the most important thing is the diversity. So as you can look around the room, even in this one classroom, there's a lot of diversity, genetic diversity that we have. So if we try and represent that with just 70% of one individual, take for instance, we have Dr. Ren be our perfect human. And we compare all of our individual genomes to his. Now, obviously, there are going to be some things that his genome will have that ours won't, ours have that his won't. So the idea is to take a number of different genomes and make an essential fusion of all those things. We can have an average of the human species genome. So obviously, that's a lot of data to process. So we'll go a little bit into the technology that they use. So they use something called SMART, single molecule real-time sequencing, which is a reversible terminal sequencing, which we learned about. So you've got different fluorescently labeled nucleotides, and they're added one at a time, and then it's taken a reading, so we can identify which nucleotide is added, and then we can continue on with the process. So we've got a short little video just to show you how that works. so anyway, there's all these different little cells, like submicron level, and each of them is like its own little reaction cell. So the strands are built in there, and they're analyzed from the bottom. And so it's a very sensitive way to analyze these. So you guys kind of get the general gist. So this group put together 15 genomes that they made their fusion from. 11 of which were newly sequenced. 3 African, 2 Asian, 2 European, 3 from the Americas, 1 South Asian, which is actually from the South India regions, and then 2 previously genomes that they had utilized. One was a hydatidiform, or 2 were hydatidiform holes, which are just abnormal human growths, which are making them haplotype, and then 2 previously studied Asian genomes. So a big part of it was the structural variants that they covered. So structural variants are defined as insertions, deletions, duplications, or inversions that are greater than 50 base pairs of lengths. So as we go through, we'll explain what the significance of these are, where they're located within the genome. So problem with the current human genome reference. These structural variants provide problems with establishing with the current reference and establishing a new reference. And one of the solutions that they're proposing is taking these 15 genomes and seeing how it compares to the reference and how it can be used as a new reference.
Each human genome was identified and sequence assembled using insertions, deletions, and inversions of base pairs of 50 or greater relative to GRCH38 using single molecule real-time sequencing. They excluded periocentromeric regions with dense tandem repeats or gap structures where we found variant call sets to be found to be unreliable. In total, this filter covers 254 million base pairs of the primary CRCH38 assembly, and per sample, it removes an average of 7,668 structural variant call sets. On average, they identified 22,755 structural variants per sample, affecting 11 million base pairs. These were then merged into a set of 99,604 non-redundant sets of structural variants, illustrated by the figure. The variants that were shared among all samples are shown in this red portion here at the bottom. The variants from each sample were merged using a non-redundant strategy, starting with CHN1 and iteratively adding unique cells from additional samples. The figure displays that the growth of the non-redundant set is initially steep, but it declines as the samples are added. This indicates the large proportion of common variation is captured by the subset of the 15 humans studied. Similarly, the set of shared variants declines quickly at first and flattens as samples are added, leaving 2,238 structural variants and 1.6 million base pairs that are observed in all samples. And the proportion of the samples carrying each variant shows a similar pattern with an increase at 100% for shared variants. They modeled the growth of the non-redundant set, excluding repetitive loci, and suggests that the addition of one more human genome would likely increase this part of the call set by 2.1%. The number of variants in each discovery class is shown per sample. These variants were then classified into 4 categories: shared when they are present in all samples, and is illustrated in red. Major is when they're present in more than 50% of the samples, but not all, and is illustrated in purple. Polymorphic is when they're in more than one, but less than half, is illustrated by dark blue. And singleton variants are when there's just one in each sample, and those are identified by this light blue at the top. The African American samples show the greatest genetic diversity, where each contributes 11.1% of the singleton variants versus 5.6% of the non-African variants. Thus, we would expect a new African sample to add approximately twice the number of novel variants compared to a non-African sample. This model supports our conclusion that additional African samples would increase the call set more sharply. The discovery class frequency for each variant type was modeled using insertions, deletions, and inversions. They identified 15,291 structural variants, accounting for 15.4% of all variants and 8.5 million base pairs total that are observed in the majority of the human genome, consisting of the shared and major alleles. This indicates that the current human reference genome carries a minor allele or an error at these positions. Compared to polymorphic variants, these majority variants tend to be larger and are enriched for the repetitive DNA. Another thing to note is that a greater proportion of the shared variants were defined as insertions with respect to GRCH38 when compared to deletions. This observation is consistent with the presence of muted gaps or regions where there is missing sequence and no indication of a gap in the reference assembly. For structural variants that were genotypical in all 440 population samples and in non-repetitive loci, the discovery frequency is shown with bars colored by genotyping support based on allele frequency. Generally, allele frequency supports genotype frequency. The graph illustrates that there is a steep decline in the number of structural variants with 0, single, and polymorphic allele frequencies as the discovery frequency increases. Major allele frequency initially declines, but then increases at a discovery frequency of around 0.5, and only major and shared or fixed allele frequencies are observed at a discovery frequency of 1.
So one of the most important things that they were kind of elucidating on was that these structural variants are not randomly distributed through the chromosome. They're actually biased towards the last 5 million base pairs of the chromosome. And this is important for a few reasons. They're actually 9 times more likely to be within 5 million base pairs from the end. That actually varies from chromosome to chromosome. The blue metacentric, that just means that the 2 halves of the chromosome are pretty much symmetric, and the acrocentric is a little bit more lopsided. So here's an ideogram of where the structural variants exist on the chromosomes. The majority actually of the structural variants are either VNTRs, which is variable number of tandem repeats, and I define that as base pairs greater than 7. And the other biggest proportion is going to be short tandem repeats, which is a little bit less. These 2 variations actually account for 70% of all the structural variations. This is just showing exactly where they are on the chromosome. An interesting thing is they actually corrected for size, and the long chromosomes still had more towards the end of them. In fact, the longer the VNTRs, the more likely it was to be towards the end of the chromosome. So this just shows different numbers of variations and how close they were towards the end of the chromosome. So a P arm is actually the short arm. So that's going to be this guy, and then the Q is going to be the long arms. There's actually a few notable differences here that kind of stand out. One is going to be how quickly chromosome 17 has structural variants, or how close to the end chromosome 17 has structural variants, especially considering it's a short chromosome. And then the 2 outliers kind of on the other end are the X chromosome, which does have long arms, and that actually does not have very many structural variants towards the end of the chromosome. The real big thing they wanted to determine by figuring out where these structural variances are on the chromosome is there a correlation between the variable number of tandem repeats or the short tandem repeats and double strand breaks and other mutations as well. But what they did find is that there actually is a correlation to where these variable number of tandem repeats are and where the double strand breaks happen. And that suggests that there's a relationship between regions prone to breakage and the formation of these variable number of tandem repeats. It didn't go into like a mechanism of why they think this happens, but there's a really pretty strong correlation between where these VNTRs are and the likelihood of that strand breaking, and then more VNTRs forming.
Alrighty. So now on to number 3, right? So we've done the first 2 of our overview. So the problem with the previously sequenced human genome using the bacterial chromosomes and plasmids is the problem of the GC heavy regions of DNA. So we know that GC heavy regions are extremely structurally stable, and we know that it's hard to break those GC regions. Like in PCR, you have to turn up the heat, you risk denaturing the compound if there's a lot of GC heavy areas. It can spontaneously form hairpin structures, which causes a problem with breaking open the DNA for replication and transcription. And of course, that is all because CG bonds have the 3 hydrogen bonds rather than the 2, as well as the bonding, the tight bonding with base stacking in terms of hydrophobic interactions, as well as hydrophobic and hydrogen bonding. So it poses a problem. It's usually not able to be transcribed in a bacterial plasmid. So they wanted to test their new structural variants with this new technology to the old sequence. And that is going to be our GRCH38 again. That's going to be that dotted line. I'm just going to call it the reference. So to figure out what the reference was missing, they wanted to see if, in fact, these structural variants were found in this GC-rich region. So what they did was they took the new structural variants, you can see your shared, your major, your polymorphic, and they put it through a bunch. They took the mean of thousands of different strands of varying length. They did significance testing, and they got this graph. And so if you remember from our GC content, anything greater than between 60 and 70% is considered a very heavy region. And so you can see kind of above here and above there is going to be your GC heavy. So these new structural variants were able to replicate and have these GC rich areas, whereas our reference there doesn't have a lot of. But the other thing that we need to pay attention to here is going to be our bimodal distribution, right? So our reference only has the 1 sharp peak. And they thought the reason for this was the tandem repeats that we just talked about. Because the tandem repeats, those GC heavy regions, even the TA heavy regions, could cause this bimodal distribution, right? So what they did to test their theory that those structural variants were in very GC-rich or poor regions was they took out all of the repeats, short and long, and they did the same testing, and what that showed was that their peak almost exactly matched the reference peak with just a small bimodal distribution. So your GC heavy content, that peak is much smaller, whereas the left skewed peak is a lot bigger. And what this tells them is the structural variants that they've identified are based heavily in these tandem repeat areas and these GC heavy areas. And so they just, once again, think that that was an artifact due to cloning and sequencing. And that's why this new method is able to find so many more new structural variants.
Filling in gaps.
Yeah. And so then what? Yeah. So that those new structural variants were able to fill in what they called gaps.
Gaps. The Human Genome Reference has 819 gaps in it. Those gaps occur where contigs are joined at what they call scaffolding switch points. And so where you join those contigs, you tend to have errors. And so what they did is they looked at all the switch points where they joined the contigs in the Human Genome Reference, and they compared them to their own smart sequencing data, and they were able to patch the Human Genome Reference. And I'll kind of briefly expand on that. So What they did was they used smart sequencing to resolve the low complexity DNA, which is this 1.6 kilobase pair CONCAT repeat in the 5' UTR. You can see here that it's actually missing from the human reference genome right here, but it's conserved in orangutans and chimpanzees. So it makes sense that it would be there, whereas where it's missing completely from the human genome reference. So they were able to resolve and patch that. Correspondingly, they were able to resolve AT-rich and AT-rich insertion. This gene is not conserved, as you can see. The human reference genome does not have it, whereas along with orangutans and chimpanzees, they also do not have it. But it's found in 2 genomes of the data they found from the smart sequencing. So they were able to resolve this AT-rich low complexity DNA with smart sequencing. Also similarly, they were able to resolve variable number tandem research or repeats / GC-rich insertions. And it's kind of hard to see here, but this is actually 3 and this is a 10. So this repeat was repeated 7 more times, whereas this one was only repeated 3 times. And so the smart sequencing was able to resolve, the 7 more repeats of variable number tandem repeats, whereas large insert DSC clones were not able to do that. So they were able to do that. And so what does this all kind of mean? If you have gaps in your genome, what's going to happen to you? Well, it turns out some of these gaps correspond to alternative splice sites, like we just learned. They were able to find in their results, but also missing from the human reference, this 150 amino acid, or also 480 base pair insertion of this low complexity DNA, and they saw that this was shared, which means it's present in all 15 of the genomes. And so if it's shared, that means it was present in all 15 of the genomes, but it was missing from the human genome reference. So they were able to patch that, and then once they patched it, they realized, hey, this is an exon, and this produces an alternative splicing site for the RRBP1 protein. And so, coincidentally, they were also able to resolve regulatory sequences. So this is not involved in encoding sequence. This is upstream of the KDM6B gene. But they were able to resolve it. As you can see, the human genome reference is missing, whereas there is a 66% GC content insert here that was patched by smart sequencing. So they were able to patch smart sequencing. And then interestingly, they talk about H3K27AC and H3K27 trimethyl. And so I guess what they did is so one's an acetylase, one's a a trimethylase. But at this point, neither are being expressed, or neither are being, the histone's not being modified here. So I think that just makes it more available for kind of this switch point resolution.
Yeah, these are some of the first modifications when initiation of transcription was happening. So.
Yeah, so that's interesting. And so what they did was, another patch that they did was they were able to recover a 200 base pair insertion in the exon 2, the coding sequence of another gene, FOXO6. And that was was missing from the human genome reference, but was conserved in chimpanzees and orangutans. So it's most likely there. They were able to resolve it. And so once they did resolve it, they realized that there are 7 loss of function variations in the FOXO6. Basically, they saw that 7 variations of the FOXO6 gene will result in loss of function. And so by using their new patching data, they were able to resolve some of these loss of function variations, and they were able to realize that, for example, what was originally a frame shift mutation is now a 3' UTR, is part of the 3' UTR. And so basically they inserted this 200 base pair insertion, or they resolved it, and that was able to find the location of the stop codon, which resulted in no more or less loss of function variation in the FOXO6 gene. And then here's our overview again. I'm just going to read it. So single molecule real-time sequencing allows for sequencing large stretches of DNA without the need to clone inserts into E. coli. Structural variants are non-randomly distributed, being biased to the last 5 mega base pairs of the human chromosome. And as structural variants were more likely to be found in GC-rich or GC-poor sequences, which were probably problematic to clone during human genome growth.
So, obviously all this is very important to our understanding more of human physiology. And so it's got developing a canonical human reference, but great benefits to being able to understand how the human genome changes over time. And it can also provide a powerful tool for tracking or establishing different genetic-related diseases. So, I mean, in the future, there's still a lot of work to be done. As technology advances, we can get more precise sequencing of the human genome. Like even the next-gen sequencing that we have, it still had its problems with single or 2-point errors. So there's a lot of growth in this field, and it'll be exciting to see in the future if they can actually establish a canonical genome reference. Thank you very much for your time and attention.
Question?
Yes, did they do any analysis on the KC content, or did they only look at KC content because of its stability?
The AT, sorry. Yeah, so that bimodal distribution. So the GC content is what they focus on, because those back clones just really don't like them. They're usually at the end of the chromosome. A lot of times when it forms that hairpin structure, the polymerase will actually break off with it. So it's really unstable. So the TA sequences, some of them were obviously missing, but they focus on the GC just because of how hard it is to clone in back plasmids and everything. So they thought that the variants that were probably most missing in the reference, the human genome reference, were probably associated with that GC stability replication thing.
One question.
So the smart, that was just the reverse terminator sequencing we talked about.
Yeah,
last?
similar to pyro sequencing, just like their proprietary.
Oh,
Reverse or pyro?
It's
Yeah.
reverse terminal.
Oh.
Yeah, it's essentially the technology is more in the cell, the way that they utilize that. Essentially is what it is.
Okay, let's thank speaker spoke for free. So if you can sign up, the function can sign here. Whenever you do something.
Yeah. Are we out of time? Oh, we are out of time.
Yeah, we got like a 5 or something in the morning when you were like just finishing up, so I think you finished.
Oh yeah, we were doing good. We did perfect on time. I think we hit 25 exact.
Flew through mine real quick.
Or don't you
Like I said on you.
Yeah, it's not.
taxes.
So no exercise.
I need these points, Red.
Let's put so we're based on this.
Okay.
Well,
So based on
so which is if you're paying in this one, you will get extra points.
Oh,
But
okay.
if you didn't pay in, which is you will not have extra points.
What if I don't have that? What if
You
I-
don't have to know your presentation,
Okay.
so you don't need it.
Just checking. Nice sweet thing.
So how if you didn't have presentation, so this is your